Hello and welcome to the World War Lab channel. Today we're diving into a moment from World War II when a quiet technological breakthrough changed everything on the battlefield, turning an ordinary tank into something the enemy never expected. September 19, 1944. A thick fog blanketed the fields near Arracourt, France. First Lieutenant Marvin M. Men of the 37th Tank Battalion tightened his grip on the rim of his Sherman's turret while his gunner stared to the periscope, slowly sweeping the misty landscape ahead. They had been warned about Panthers, the fearsome German tanks whose sloped armor had already earned a reputation for being nearly immune to standard American shells. What Men and his crew didn't realize was that hidden inside their ammunition rack were 6 rounds that had the potential to rewrite the rules of armored combat. 6 M93 high-velocity armor-piercing rounds, each built around a tungsten-carbide core, capable of turning their medium Sherman into something German tankers would soon come to fear. The psychological shock of this ammunition would prove almost as destructive as its physical power, shattering long-held German assumptions about American tank capabilities and forcing a complete rethinking of the Panther's supposed invulnerability. The story of how a specialized type of ammunition shifted the balance of armored warfare begins not in the fields of France, but in the testing ranges and industrial plants of the United States. There, metallurgists and ballistic engineers were racing against time to solve a problem that threatened to cripple American armored operations in Europe. By early 1944, the U.S. Army faced a dilemma its planners had not fully anticipated. The M4 Sherman, the backbone of American armored divisions, was encountering German tanks it could not reliably defeat from the front. The Panther, Germany's answer to the Soviet T-34, combined a powerful high-velocity 75mm gun with an 80mm glacis plate sloped at 55 degrees, giving it an effective armor thickness of roughly 140mm. This made it nearly impervious to the weapons most American tanks carried. American intelligence had underestimated both how many Panthers would appear and how capable they would be. By June 1944, when Allied forces stormed the beaches of Normandy, Panthers made up 38% of all German tanks in the theater. Not a handful, as predicted, but hundreds of these advanced medium tanks. Many were crewed by relatively inexperienced soldiers, yet they were protected by armor that American tank guns simply could not penetrate head-on. The 75mm M3 gun that armed most Shermans in Normandy was completely incapable of piercing a Panther's frontal armor at any range. Shells would strike the slope glacis and bounce away, leaving Sherman crews exposed to devastating return fire. The Panther's gun, by contrast, could destroy a Sherman from distances exceeding 2,000 meters. Even the improved 76mm M1 gun, which began reaching frontline units in July 1944, struggled against the Panther. Firing the standard M62 armor-piercing capped rounds, the 76mm gun could penetrate about 109mm of armor at 1,000 meters at 0 degrees of obliquity. This was effective against the Panzer IV and many German assault guns, but it was still not enough to deal with the Panther's sloped frontal armor. The 76mm could penetrate the Panther's gun mantlet, but only at extremely close range, often under 100 meters. At such distances, engaging a Panther was nearly suicidal, given its superior firepower and protection. The problem was not the gun itself, but the ammunition it fired. The introduction of the 76mm gun had already been delayed by a long saga of bureaucratic hesitation and misplaced confidence. The first M4 Shermans equipped with the 76mm M1 gun rolled off production lines in January 1944. These M4 A176 Shermans arrived in Britain on April 10, 1944, with 130 tanks delivered in preparation for the Normandy invasion. Yet, despite their availability, American commanders chose not to deploy them on D-Day. Several reasons were given. Tank crews had not been given enough time to train on the new weapon system. Logistical officers worried about the complications of supplying 2 different types of tank ammunition. Most importantly, Many commanders believed the existing 75mm gun would be sufficient against whatever German armor they expected to face. This belief turned out to be a catastrophic misjudgment. By early July 1944, reports coming in from Normandy painted a grim picture. On July 2nd, complaints about the complete ineffectiveness of the 75mm gun against German armor reached General Dwight D. Eisenhower himself. His response, recorded in several historical accounts, reflected the frustration at the highest levels of command. "You mean our 76 won't knock these Panthers out? Why? I thought it was going to be the wonder gun of the war." Witnesses later recalled that his full statement included much stronger language, expressing anger that the Ordnance Department had assured him the 76mm gun would handle anything the Germans could field. A special board convened on July 12, 1944, and officially confirmed what tank crews already knew through bitter experience. Standard American weapons could not defeat the Panther frontally. General Omar Bradley immediately ordered that the 76mm Shermans be rushed from Britain to the front lines. On July 25, 1944, during Operation Cobra, 102 M4A1-76 tanks finally saw combat. The first reports from these engagements were sobering. Although the 76mm gun was an improvement over the 75mm, it still struggled against the Panther's frontal armor at normal combat distances. Sherman crews quickly learned that they had to maneuver for side shots or attempt dangerous close-range attacks on the Panther's gun mantlet. Neither option was tactically attractive when facing a tank that could destroy them from more than 2 kilometers away. The real solution would come not from tactics alone, but from metallurgy and physics. By July 1944, American ordnance engineers had developed a new type of ammunition known initially as the T4 round, later standardized as the M93 HVAP, or a high-velocity armor-piercing round. This ammunition represented a radical departure from traditional armor-piercing design. Instead of relying on a full-caliber steel projectile, the M93 used a dense tungsten carbide core, one of the hardest materials available at the time. This core was surrounded by a lightweight aluminum body and capped with a ballistic windshield. The design focused the projectile's kinetic energy into a much smaller, denser penetrator while reducing the overall weight of the round. The results were extraordinary. The M93 achieved a muzzle velocity of 1,036 meters per second, compared to just 792 meters per second for the standard M62 armor-piercing round. This increase of 244 meters per second in velocity translated directly into a dramatic jump in penetrating power. At a range of 1,000 yards, roughly 914 meters, the HVAP round could penetrate up to 160 millimeters of armor at 10 degrees of obliquity. According to official War Department testing data, this meant that even the Panther's gun mantlet, made from curved cast steel and measuring about 100 millimeters thick on early D and variants, and later increased to 120 millimeters on the G variant, could now be reliably penetrated. What had once required point-blank range suddenly became possible at distances approaching 1,000 meters. The mantlet, previously an impractical target, became a realistic and tactically viable aim point for Sherman crews who had earlier been forced to attempt desperate flanking maneuvers or withdraw entirely. But the development of HVAP ammunition solved only half the problem. The other half was production. The T4 round depended on tungsten carbide, a strategically vital material that was in extremely limited supply. Before the war, China had produced about 36% of the world's tungsten, making it the primary source for Allied needs. Tungsten was essential not only for HVAP ammunition, but also for machine tools, armor-piercing rounds of many calibers, armor plate hardening, and numerous industrial processes. All of these applications were competing for the same scarce resource. American demand for HVAP ammunition alone consumed hundreds of metric tons of tungsten each year. Every single 76mm HVAP round required about 0.88 kilograms of tungsten carbide, meaning that a single Sherman carrying just 6 rounds needed nearly 5 kilograms of this rare material. China produced approximately 10,000 metric tons of tungsten concentrates in 1944, but that supply had to satisfy the needs of all allied industries and all military applications. The United States tried to supplement Chinese imports with domestic production from small deposits in Colorado, Nevada, and California, but total availability remained sharply limited. Germany's situation was even worse. Swedish tungsten imports declined rapidly as the war turned against the Reich, and domestic production was minimal. By 1945, German factories were hoarding what little tungsten they had for machine tools needed in aircraft engine production, while Panther crews continued to receive only standard ammunition. The U.S. Ordnance Department had been testing HVAP projectiles as early as the spring of 1942, but full-scale production did not begin until after the Normandy campaign exposed just how serious the Panther threat really was. In July 1944, production of 3-inch HVAP rounds for tank destroyers reached only 1,000 rounds. In August, 1,000 rounds of 76mm HVAP were produced. September yielded another 1,000 rounds of 76mm ammunition. It was not until November 1944 that monthly production reached 5,000 rounds for the 76mm gun, and only by January 1945 did output rise to about 7,000 rounds per month. By March 1945, roughly 33,000 rounds of 76mm HVAP ammunition had been manufactured. This represented an enormous industrial effort, but it was still only a fraction of what was required. By February 1945, the average 76mm Sherman in Europe had received a total of just 5 HVAP rounds. 5 rounds to face an enemy that now fielded Panthers as the standard tank in its Panzer divisions. A Sherman company with 17 tanks would therefore possess only 85 HVAP rounds in total, while facing German formations that might deploy 30 or more Panthers. The imbalance was stark. The first HVAP rounds reached the European theater in August 1944, but their arrival was overshadowed by broader tactical realities. In Normandy, the thick hedgerows had forced American armor into close-quarters fighting where German guns held a decisive advantage. Panthers were positioned in ambush sites where their long-range firepower could dominate narrow lanes of approach. Crews learned to exploit hull-down positions, exposing only the heavily armored turret, while keeping more vulnerable hull hidden. German doctrine emphasized first-shot capability, with Panthers waiting in prepared positions and allowing Sherman columns to advance into killing zones before opening fire from distances at which American return fire was ineffective. The psychological effect on American tank crews was severe. The Sherman earned the grim nickname the Ronson, based on the claim that it lit every time. While later analysis showed this reputation was exaggerated, the belief itself shaped behavior on the battlefield. When Sherman commanders spotted Panthers, they often chose to call for artillery or air strikes instead of engaging directly. In doing so, they surrendered tactical initiative to an enemy who, with the right ammunition and proper tactics, could be fought more effectively. The arrival of HVAP round began to change this balance, but progress was slow, hampered by shortages of ammunition and a lack of training on its true capabilities and limitations. The first major combat test of HVAP ammunition did not occur in the hedgerows of Normandy, but in the open terrain of Lorraine. There, American armored divisions had broken into country that better suited German defensive doctrine. By September 1944, Lieutenant General George Patton's Third Army was deep in France, racing toward the German border with supply lines stretched almost to the breaking point. The 4th Armored Division, one of the most aggressive and effective American formations, had advanced rapidly and seized a bridgehead across the Moselle River near Arracourt. German High Command recognized the danger immediately. If Patton's armor reached the Rhine and crossed into Germany, the industrial heartland of the Reich would be exposed. General Otto von Manschenfeld's 5th Panzer Army received orders to counterattack, destroy the American bridgehead, and halt Patton's advance. The German force assembled for this mission included 2 newly formed panzer brigades, the 111th and the 113th, equipped largely with Panther tanks fresh from the factories. On paper, the German advantage appeared overwhelming. Together, the two brigades fielded roughly 150 tanks, while Combat Command A of the 4th Armored Division had only about 50 Sherman tanks. The 113th Panzer Brigade alone entered the battle with approximately 90 tanks and assault guns across its two battalions, including 42 Panthers and around 40 Panzer IVs. German planners fully expected a rapid and decisive victory. The technical superiority of the Panther was supposed to compensate for any American advantages in logistics or air support. That belief was fundamentally mistaken. The Battle of Arracourt, fought over 11 days from September 18th to September 29th, would become the largest tank battle involving American forces until the Battle of the Bulge. More importantly, it would prove that American tank crews, when properly trained and equipped, could defeat technically superior German armor through better tactics, effective combined arms coordination, and careful use of high-velocity armor-piercing ammunition. The morning of September 19th opened with dense fog covering the rolling countryside around Arracourt. German reconnaissance was severely limited. The Panzer brigades, lacking adequate scouting elements, advanced blindly into terrain held by American units that knew the ground well and had already prepared defensive positions. At around 8 a.m., elements of the 113th Panzer Brigade pushed through American outposts east and south of Arracourt. The German tanks, factory-fresh Panthers crewed by inexperienced soldiers, moved forward in column formation, a serious tactical mistake that seasoned American tankers immediately recognized and prepared to exploit. Captain Kenneth R. Lamison C Company of the 37th Tank Battalion was positioned along key approaches to Arracourt. His Sherman crews had been briefed on the HVAP rounds now carried in their ammunition racks. 6 rounds per tank. The instructions had been clear. Use them sparingly and only against Panther turrets or mantlets, and only at ranges where velocity would still be high enough to ensure penetration. The fog that hindered German reconnaissance now worked to the Americans' advantage. A section of Lamison's Shermans was positioned south of the village when the first Panther suddenly emerged from the mist at a distance of barely 75 meters. At that range, the Panther's superior long-range firepower meant nothing. The American gunner fired immediately. The HVAP round, traveling at over 1,000 meters per second, struck the Panther's gun mantlet. The tungsten-core core punched through the curved cast steel and detonated the ammunition stored beneath the gun breech. The Panther erupted in a violent explosion, its turret lifting slightly from the force of the secondary blast. 2 more Panthers appeared moments later. Both were destroyed within seconds, their crews unable to return effective fire in the poor visibility. The remaining German tanks turned away, their crews stunned by the sudden loss of 3 Panthers to what they had been taught were inferior American tanks. Throughout the morning of September 19th, similar engagements unfolded across the Arracourt sector. American tanks used the fog as concealment, engaging Panthers at distances where HVAP rounds were at their most effective. German tactical deployment repeatedly proved disastrous. Advancing in column without proper reconnaissance, Panther crews exposed their thinner side armor to American flanking fire again and again. Near the Arracourt command post, a platoon of M18 Hellcat tank destroyers, also armed with 76mm guns and HVAP ammunition, clashed with German armor at close range. The fast-moving Hellcats were devastating in the fog-shrouded fighting, striking quickly and relocating before German crews could react. By noon, as the fog began to lift, American forward artillery observers were able to coordinate fire more effectively with defending tank companies. P-47 Thunderbolt fighter bombers from a 405th Fighter Group soon appeared overhead, diving through breaks in the clouds to attack German armor with rockets and heavy machine gun fire. The full extent of the American advantage now became clear. While the Panther was superior as an individual weapon system, American forces fought using combined arms as standard practice. German tanks advanced without sufficient artillery support, without air cover, and without infantry to clear American defensive positions, American units. By contrast, integrated tanks, artillery, infantry tank destroyers, and air power into a unified system that overwhelmed German technical advantages. When Panthers encountered these repair defenses, they were destroyed one by one despite their formidable specifications. The HVAP ammunition did not make the Sherman equal to Panther in terms of armor or gunpowder on paper. But warfare is not decided by technical charts alone. Tanks are destroyed by crews who understand how to exploit weaknesses under real combat conditions. The Panther's gun mantlet, necessary to allow the 75mm gun to elevate and traverse, created a vulnerable point, the junction between turret and hull. The thinner side armor and the engine deck were all targets that HVAP-armed Shermans could now successfully engage at ranges that had once been considered suicidal. Even more damaging to German morale was the psychological shock of discovering their armor was no longer invulnerable. Panther crews had been trained to believe that American tanks could not penetrate them from the front. Intelligence briefings emphasized the Sherman's supposed inferiority. Crews were told that as long as they kept their frontal armor facing the enemy, they were safe. The first commanders who watch American rounds punch through their mantlets and ignite their ready ammunition learned otherwise in the most brutal way possible. Survivors carried this knowledge back to their units, spreading the realization that American tanks now possessed ammunition capable of defeating Panthers. By the afternoon of September 19th, German tank commanders were reporting to headquarters that Shermans were using new, far more powerful ammunition. The reports were confused and often contradictory. Some claimed the Americans had secretly deployed tank destroyers armed with 90mm guns. Others suggested that British 17-pounder Firefly tanks had been attached to American units. The truth was more disturbing. American industry had developed a specialized type of ammunition that partially neutralized the Panther's armor advantage. For German planners, this was more alarming than any of the alternative explanations. It meant that American industrial capacity could respond to battlefield problems faster than German industry could adapt. It meant that technical superiority could no longer be relied upon as a guarantee of battlefield dominance. The fighting continued through September 22nd, when the main German offensive effort finally stalled. By that point, American forces had destroyed or disabled approximately 86 German tanks and assault guns. American losses stood at 25 Sherman tanks and 7 tank destroyers. The kill ratio heavily favored the Americans despite their technical disadvantage in performance of individual tanks. The Battle of Arracourt was not only a tactical victory, but also a psychological turning point. American tank crews discovered that they could defeat Panthers without waiting for specialized tank destroyers or relying entirely on overwhelming air support. At the same time, German crews lost a sense of security that came from believing in absolute frontal invulnerability. From the German perspective, Arracourt was marked by confusion and bitter recrimination. The 113th Panzer Brigade, which had entered the battle with roughly 90 tanks and assault guns, could muster fewer than 20 operational vehicles by September 29th. German after-action reports struggled to explain how such a comprehensive defeat had occurred. On paper, the Panther's technical superiority was unquestionable. How, then, had newly built tanks, even with inexperienced crews, been defeated so decisively? Part of the explanation lay in training and experience. The Panzer Brigade crews had received minimal preparation, often arriving at the front after only a few weeks of instruction. In contrast, American tank crews of the 4th Armored Division were seasoned veterans who had fought their way across France. They understood combined arms warfare and knew how to read terrain for tactical advantage. But training alone could not explain the penetrations that should have been impossible with standard American ammunition. German intelligence officers examining destroyed Panthers noticed entry holes that were smaller than expected, indicating the use of a subcaliber projectile. When unexploded rounds were recovered near disabled tanks and analyzed, the truth became clear. The Americans had deployed tungsten-core ammunition. This discovery carried major strategic implications. Germany itself had developed similar rounds, the Panzer Granate 40, which also relied on tungsten cores to increase penetration. However, by late 1944, German tungsten supplies were critically limited, and what remained was being reserved primarily for machine tools rather than ammunition production. If the Americans could field tungsten-core ammunition in quantity sufficient to distribute to frontline tank units, it demonstrated an industrial capacity and access to resources that Germany simply could not match. American tanks were not only more numerous and better supported logistically, but they were now equipped with ammunition that partially negated Germany's carefully engineered advantage in armor protection. The influence of HVAP ammunition extended far beyond the immediate tactical results at Arracourt. As news spread through American armored units that this new ammunition could defeat Panthers under the right conditions, tank crews became more willing to engage German armor directly. The psychological paralysis that had gripped some units during the brutal fighting in Normandy began to fade. Crews still respected the Panthers' capabilities, but they no longer felt helpless against it. This shift in morale was critical. A crew that believes it can fight will maneuver aggressively, seek favorable positions, and take calculated risks. A crew that believes it is outmatched will hesitate, surrendering the initiative to the enemy. HVAP ammunition, even in critically short supply, gave American tankers a weapon that allowed them to face Panthers on more equal terms. Even crews that never fired a single HVAP round benefited psychologically from knowing that such ammunition existed and might be available in moments of greatest need. The scarcity of HVAP forced commanders to make difficult decisions. Tank destroyer units, whose primary mission was anti-armor combat, were usually given priority. Sherman units, which had to balance infantry support with engaging enemy armor, often received fewer rounds despite encountering German tanks more frequently. This created tension between tactical necessity and logistical reality. Allocation was managed at several command levels, from Army headquarters down to battalions, and the system was far from efficient. Some units received more HVAP than they could immediately use, while others burned through their supply within days and were unable to obtain resupply even after urgent requests. When German forces launched their surprise offensive in the Ardennes in December 1944, American armored units once again faced intense pressure. The Battle of the Bulge saw hundreds of Panthers and Tiger tanks committed to combat under winter conditions that favored defense and limited Allied air support because of persistent bad weather. Sherman crews depended heavily on their scarce HVAP ammunition to engage German heavy armor. Shortages became critical within days. Some units exhausted their HVAP entirely and found their resupply requests unanswered as logistics networks struggled to function through snow-blocked roads and areas disrupted by the German advance. Even under these conditions, American forces demonstrated that tactical skill and combined arms coordination could compensate for technical inferiority. Tank crews worked closely with infantry, using bazooka teams to disable Panthers at close range while Shermans provided covering fire. Artillery forward observers called in time-on-target missions that shattered optics, damaged tracks, and killed exposed crewmen even when shells could not penetrate armor. When weather conditions finally improved in late December and January, Allied air power proved devastating. Attacking German armor concentrated along roads and supply routes. The Battle of the Bulge ended with German armored forces shattered. Hundreds of tanks and, more importantly, irreplaceable veteran crews had been lost in an offensive that failed to achieve its objectives. By early 1945, the strategic situation had shifted decisively and irreversibly in favor of the Allies. American and British forces were preparing to cross the Rhine. Soviet armies were advancing relentlessly from the east, having broken through German defenses in massive winter offensives. Germany's industrial capacity was collapsing under the combined weight of strategic bombing, the loss of territory containing critical resources and factories, and severe shortages of raw materials, including fuel and tungsten. Panther production, which had reached approximately 3,900 units in 1944, declined sharply in early 1945 as factories were destroyed, transportation networks were disrupted, and supply chains began to unravel. As raw materials became increasingly unavailable, even newly built Panthers often never reached the battlefield. Fuel shortages were so severe that many German tanks remained immobile. In the final months of the war, German armored units frequently abandoned perfectly functional vehicles not because of combat damage, but simply because they had no fuel to operate them. The technical limitations of HVAP ammunition, although far less discussed than its successes, are essential for complete historical understanding. The tungsten carbide core, while extremely effective at penetrating armor under favorable conditions, was inherently brittle. Below certain impact velocities, roughly between 2,300 and 2,500 feet per second, the core could shatter on contact rather than penetrate. This meant that HVAP effectiveness dropped sharply at longer ranges where projectile velocity had decreased. Against Panther gun mantlets, the effective range was about 1,000 meters. Beyond that distance, the probability of the core breaking apart on impact rose significantly. American tank crews learned these limitations through direct combat experience, sometimes at high cost. Firing HVAP at Panthers beyond its effective range wasted extremely scarce ammunition and often invited deadly return fire from German guns that remained lethal at far greater distances. Training on the proper use of HVAP was frequently inadequate, as the ammunition arrived at frontline units faster than manuals and instructional materials could be produced. Many crews learned how to employ it correctly only through trial and error under combat conditions. Sergeant Francis Baker's documented experience on November 20th, 1944, illustrated both the promise and the limits of HVAP in real combat. His Sherman, armed with a 76mm gun and carrying HVAP rounds, engaged a Panther at approximately 800 yards. Baker's gunner fired at least 7 rounds, with multiple hits clearly observed on the Panther's side armor. To Baker's frustration, the rounds bounced off without achieving penetration. The engagement showed that even HVAP had serious limitations, especially against sloped armor struck at oblique angles. The Panther eventually withdrew rather than continuing the fight, so the action was not a complete tactical failure, but reminded Sherman crews that HVAP was not a magical solution. Proper tactics, accurate range estimation, careful shot placement, and favorable engagement angles remain absolutely critical. HVAP gave American tankers better odds, but success still depended on skill, experience, and judgment. Post-war analysis of HVAP ammunition confirmed both its strengths and weaknesses. Against the Panther's gun mantlet at ranges up to 1,000 meters, HVAP was highly effective when hits were achieved, reliably penetrating and often triggering catastrophic secondary explosions inside the tank. Against a glassy plate, however, results were poor except at extremely close ranges and under favorable impact angles. The extreme slope of the Panther's frontal armor meant that even tungsten-core rounds traveling at high velocity frequently ricocheted or shattered on impact. Sherman crews still had to maneuver for better angles, flanking Panthers whenever possible. HVAP did not make Sherman's technical equals to Panthers, but it gave American crews a fighting chance in situations where frontal penetration had once been almost impossible. The Korean War, which began in June 1950, provided another opportunity to evaluate HVAP in combat. By then, American Shermans, primarily the M4A3E8 variant armed with 76mm guns, faced Soviet-built T-3485 tanks used by North Korean and later Chinese forces. Unlike in Europe, where HVAP had been critically scarce, tungsten supplies by 1950 were no longer constrained by wartime competition, and large stockpiles were readily available. American crews in Korea discovered that HVAP rounds easily penetrated T-3485 armor at standard combat ranges. The T-3485, while a capable tank, had armor protection far inferior to that of the Panther. Its turret front, roughly 90 millimeters thick, and its 45 millimeters glassy plate could not resist high-velocity tungsten-core projectiles fired from 76mm guns. As a result, American Shermans in Korea achieved highly favorable exchange ratios against communist armor. This success was due in part to superior crew training, but also significantly to the abundant availability of HVAP ammunition. For veterans of the European theater, this outcome was bittersweet. The ammunition that had been so scarce in 1944 and 1945, and which could have saved many lives, proved devastatingly effective in Asia once supply limitations were removed. What had been a rare and tightly rationed resource in Europe became a standard and reliable tool in Korea. Post-war German perspectives on American HVAP ammunition, drawn from interrogations and captured documents, revealed a mix of reluctant respect and deep frustration. German ordnance officers acknowledged that American industry had solved the problem of tungsten-core ammunition more effectively than Germany had. Although Germany had pioneered the basic concept with its Panzer Granite 40 series, production constraints meant those rounds were never available in sufficient quantities. American production of HVAP, while still limited by tungsten shortages, far surpassed German capability by late 1944. German tank crews interviewed after the war often cited improvements in American ammunition as a major factor that complicated their tactical situation. Once it became clear that Shermans could penetrate Panther mantlets at combat ranges, German crews could no longer rely on frontal armor as an absolute shield. This forced them into more cautious tactics, slower advances, and heavy reliance on defensive positions. But defensive warfare surrendered initiative to American forces, allowing them to employ combined arms tactics that steadily eroded German advantages. The psychological impact of losing their sense of armor and vulnerability contributed to the increasingly defensive mindset that defined German armored operations in 1945. The Panther, once seen as an untouchable symbol of technical superiority, had become just another weapon system, vulnerable when confronted by skilled crews, coordinated tactics, and ammunition specifically designed to exploit its weaknesses. Technical analysis of HVAP projectiles recovered from destroyed German tanks gave German engineers a clear understanding of how American ammunition was designed. The tungsten carbide core, surrounded by a lightweight aluminum carrier body, represented an efficient use of scarce strategic materials. It maximized penetrating power while minimizing the amount of tungsten required for each round. The lightweight carrier allowed higher muzzle velocities without causing excessive barrel wear, while the dense tungsten core retained kinetic energy far more effectively over distance than conventional steel penetrators. German engineers immediately recognized the advantages of this design, but they lacked both the industrial capacity and the material resources to respond with similar developments. By late 1944, German tank and ammunition production was focused entirely on maintaining output of existing designs rather than introducing new ammunition types. The Panther's KWK 42-75mm gun already had excellent penetration against Allied tanks when firing standard ammunition, so improving German rounds was not viewed as an urgent priority. More importantly, developing new tungsten-based ammunition would have required materials Germany simply could not spare and factory retooling that was impossible under the constant pressure of Allied air attacks. As a result, German tanks in the final year of the war continued to fight with ammunition designs dating back to 1942 and 1943, while American ammunition technology continued to evolve. The historical importance of the Battle of Arracourt extended far beyond its immediate tactical outcome. The engagement demonstrated conclusively that American armor doctrine, which emphasized mobility, combined arms coordination, superior logistics, and overwhelming material support, could consistently defeat German methods that relied heavily on the technical superiority of individual tanks. German commanders had designed their 1944 Panzer brigades around the Panther's capabilities, assuming that armor protection and firepower would compensate for inexperienced crews and limited supporting forces. This assumption proved catastrophically wrong. The lesson was clear to military observers on both sides. Technical excellence in weapon design mattered and could provide real advantages, but operational excellence in combined arms warfare, logistics, and training mattered more in achieving tactical and operational success. HVAP ammunition illustrated this perfectly. It was not a miracle weapon, but when combined with proper tactics and coordination, it shifted the balance in critical situations. The effect of HVAP on individual tank crews went far beyond purely technical considerations. For American tankers who had faced Panthers in Normandy using only standard ammunition, the arrival of HVAP represented something tangible and deeply personal: hope. The ammunition did not eliminate the Panther threat, but it gave them a realistic chance of penetrating German armor under favorable conditions. That knowledge alone improved morale and encouraged more aggressive and confident tactics. For German tankers, the effect was the opposite. The realization that American tanks could now pose a credible frontal threat fundamentally altered their tactical calculations. Otto Carius, one of Germany's most highly decorated tank commanders who survived the war and later wrote extensively about his experiences, emphasized how crucial the sense of invulnerability was to crew morale. Thick armor gave crews confidence and encouraged aggressive action. Once that sense of invulnerability was lost, performance suffered. Panther crews facing Shermans equipped with HVAP experienced exactly this erosion of confidence. The gun mantlet became a known weak point that competent American gunners could exploit. This knowledge made Panther crews more cautious, slower to commit, and generally less willing to take tactical risks. The strategic implications of HVAP development extend into broader questions about technological competition in modern warfare and the importance of industrial capacity. Both American and German research establishments had skilled engineers and a sophisticated understanding of ballistics and armor penetration. Both recognized the value of tungsten-core ammunition early in the war, and both developed workable designs. The difference was not scientific knowledge, but industrial power and access to resources. American industry could produce HVAP in quantities large enough to influence battlefield outcomes, even if never in sufficient numbers to fully equip all units. German industry could barely produce enough to conduct testing. This pattern appeared repeatedly throughout the war. Germany often developed highly sophisticated and technically impressive weapons, but lacked the industrial base to manufacture them in numbers that could change the strategic balance. The United States, by contrast, produced equipment that was sometimes less technically refined but highly reliable, supported by massive logistics, and built in overwhelming numbers. The M4 Sherman was not the best tank of World War II by most technical standards, but American factories produced approximately 49,324 Shermans, compared to about 6,132 Panthers. This reduction ratio of roughly 8-to-1, combined with ammunition improvements like HVAP that narrowed the technical gap, proved strategically decisive. The post-war careers of those who fought at Arracourt reflected how deeply these lessons shaped military thinking. Lieutenant Colonel Creighton Abrams, who commanded the 37th Tank Battalion with distinction during the battle, later rose to become Chief of Staff of the United States Army and gave his name to the M1 Abrams main battle tank. The lessons he learned about combined arms warfare, the critical importance of crew training, and the necessity of adequate and advanced ammunition influenced his entire career and the doctrine he helped shape. The M1 Abrams was deliberately designed with a powerful 120mm smoothbore gun and advanced ammunition types, including depleted uranium penetrators that serve essentially the same function as HVAP did during World War II. German veterans who survived Panther units and later joined the West German Bundeswehr carried different but equally important lessons. They had personally experienced the limits of possessing technologically superior equipment without the industrial base and logistics to sustain it. During the Cold War, Bundeswehr armored doctrine emphasized high-quality equipment and exceptional training, while openly recognizing that West Germany could not hope to match the numerical strength of potential adversaries. But planners in the Bundeswehr, informed by their wartime experience, also placed strong emphasis on ammunition effectiveness. The Leopard 1 and later the Leopard 2 main battle tanks were equipped with highly sophisticated ammunition designs, shaped by the understanding that ammunition technology and crew training were just as important as armor thickness itself. The end of World War II in Europe, marked by Germany's unconditional surrender on May 8, 1945, eliminated the immediate tactical need for HVAP ammunition against Panthers. In the aftermath, American ordnance officers conducted systematic examinations of destroyed German vehicles. On several wrecks, they found clear evidence of HVAP penetrations, confirming the ammunition's effectiveness under favorable conditions while also reinforcing its limitations. Panther struck by HVAP typically showed penetrations through the gun mantlet or the turret face when hit at advantageous angles, but rarely through the glassy plate, which remained highly resistant. This pattern validated American tactical doctrine that stressed flanking maneuvers and the creation of favorable engagement angles rather than reliance on frontal attacks. Comprehensive post-war analysis concluded that while HVAP significantly improved the Sherman's ability to deal with heavy German armor, the truly decisive factors in the Allied victory were overwhelming numerical superiority, vastly superior logistics, total air dominance, powerful and responsive artillery support, and more effective operational doctrine. The evolution of American tank crews from mid-1944 to early 1945 reflected the cumulative effect of combat experience, better equipment availability, and growing familiarity with specialized ammunition such as HVAP. Tank crews who landed in Normandy in June 1944 often felt genuine apprehension when facing German armor, especially Panthers and Tigers. By early 1945, after months of hard combat, improvements in training, greater numbers of 76mm Shermans, and increasing experience with HVAP ammunition, American tankers approached engagements with far greater confidence. This psychological transformation had direct tactical consequences. Confident crews fought more aggressively, recognized opportunities faster, accepted calculated risks, and exploited battlefield advantages more effectively. HVAP ammunition alone did not create this change, but its availability and proven performance contributed meaningfully to improved morale and combat effectiveness. The legacy of HVAP development continues to shape modern ammunition design. American armor doctrine, after 1945, consistently emphasized ammunition effectiveness as a central component of tank performance. Modern tank rounds use depleted uranium or advanced tungsten alloys, materials chosen for the same fundamental properties that made tungsten carbide so effective during World War II: extreme density and hardness. The guiding principle remains unchanged: concentrate maximum kinetic energy into a small, extremely dense projectile traveling at the highest possible velocity. The continuity from the HVAP of 1944 to today's armor-piercing, fin-stabilized, discarding sabot ammunition demonstrates how deeply World War II lessons still influence military technology. Soviet and later Russian tank ammunition development followed a remarkably similar path, independently reaching the same conclusions. Armor penetration depends heavily on projectile material properties and the efficient delivery of kinetic energy. In this sense, the global tank ammunition industry traces much of its technological lineage to the HVAP experience, when engineers first demonstrated conclusively that specialized ammunition could partially overcome advantages in armor protection. September 19, 1944, when First Lieutenant Merwin Men's Sherman crews first engaged Panthers with HVAP ammunition at Arracourt, marked a genuine turning point in the psychological balance of armored warfare. German crews, who had fought with confidence behind their armor, learned that American tanks could now pose a serious frontal threat. American crews, who had often felt outmatched, gained confidence from knowing they possessed ammunition capable of defeating Panthers under favorable conditions. This shift in tactical psychology, made possible by tungsten-core ammunition produced in American factories, influenced every subsequent armored engagement in the European War. HVAP ammunition, though never available in the quantities commanders desired, provided enough added capability to transform American tank crews from cautious defenders into confident attackers willing to engage German armor directly. The crews who fired those first HVAP rounds and watched tungsten cores punch through armor that had once seemed invincible demonstrated something far larger than a technical achievement. They proved that industrial capacity and material science, applied intelligently to urgent tactical problems, could overcome what appear to be insurmountable technological disadvantages. This fundamental lesson, learned at tremendous cost on the battlefields of Europe, remains directly relevant to military planners confronting the technological challenges of modern warfare.